So if we want to be able to identify horizontal asymptotes, what we need to pay attention to is the degree of the numerator and the degree of the denominator, where this happens in three potential cases. Either we have that the degree of the numerator is higher, where if that happens, there aren't any horizontal asymptotes. If the degrees are equal, then there is a horizontal asymptote at the value given by the leading coefficient of the numerator over the leading coefficient of the denominator. And then finally, if the degree of the denominator is higher, then there will be one along the x-axis or the line y equals 0. Or you can think about what happens in each of these cases as a bit of a thing called the law of large numbers, that says that as x gets really big, the largest powers on the top and bottom are really what will define everything in terms of the function's overall behavior. If the top has bigger powers, then the top is going to dominate. So as x goes to infinity, that one's going to be the more important one, and it's just going to drag everything away, not towards a specific place. If they are the same, then all it's going to matter is the ones on top that match up. They are going to squeeze between themselves and end up forming their own spot that they get closer and closer to. And then if the bottom's bigger, that's going to mean that everything's going to get dragged down over time by that large denominator, tending towards 0. And we'll see what this looks like with a couple of examples here. So for this, we want to identify the horizontal asymptotes, should they exist, of the functions 9x squared over 3x squared plus 1, 9x over 3x squared plus 1, and 9x cubed over 3x squared plus 1. So in the first case, what we have to note there is that the degree of p is equal to 2 in that case, which is equal to the degree of q. But remember, we call p the one on top and q the one on the bottom. So because these degrees are the same, we're in that first case we talked about, so we have a horizontal asymptote, and I'm going to abbreviate that like so, at the ratio of the leading coefficients, which here would be 9 over 3. So, or if you prefer, as most people would, 3, which we can graph like so, getting that weird sort of bowl shape with the asymptotic behavior noted at y equals 3. Meanwhile, in the second case, because we have that the degree of p is equal to 1, and that is smaller than the degree of q, which is 2, that means we have a horizontal asymptote at the line, getting ahead of myself, at y equals 0. That is, we have one along the axis because the degree of the bottom is bigger. That bottom part is going to drag everything down, and we'll end up with a shape something like this in that case with our noted asymptotic behavior. And then finally, for our third case, there's not a whole lot of space for it, unfortunately. I might have to get a little bit creative with where I put my images. We have that the degree of p there is equal to 3, which is bigger than the degree of q, which I don't know why I reorganized that, but that's okay. That's bigger than the degree of q, which is 2. So, in that case, we do not have a horizontal asymptote, because what happens on top will drag away what happens on the bottom as x gets really large. It's not going to matter, and we'll have a shape that looks something like a cubic function. Not quite cubic, because you've got other things going on there in a sense, but roughly that's what's going on, which doesn't indicate any asymptote at all. And in particular, well, we might have a vertical asymptote in terms of, actually no, we wouldn't have a vertical asymptote. I misread that there, because we would have that square that causes non-real things. Nah, no asymptotes at all, actually. It just does whatever it wants. And the very last thing we're going to get here for this section for this week is talking about a brief application for how we can use this sort of thing.